if two triangles have two sides equal to two sides respectively, and also have the base equal to the base, then they also have the angles equal, which are contained by the equal straight lines. So this is essentially the side-side-side congruency theorem, even though Euclid really didn't think of it in terms of congruency. But let's just say we have two triangles, and it's saying that ABC, let's just call it ABC, DEF. Okay, now assume this is equal to that side's equal to that side, and the base is equal to the base. So let's assume this is equal to the base, and this is equal to the base. So he's arguing that the two triangles must be congruent. You're able to place one exactly on top of the other. And yes, he essentially uses the superposition argument, however, he kind of does use the previous proposition to prove this. Because he's saying, let's assume that they're not congruent, which means they will not overlap, right? So, here's BC, right? Here's BC. So let's put EF right where BC is. So, I mean, it makes sense that it'll fit right on BC. It's the exact same line, right? Same length. Now, we're arguing that, I mean, I'm going to change the triangles just for the sake of argument, just to make a point, right? This is triangle ABC. I know that's not how it looks like, but let's assume that's the triangle. We're trying to argue that if we placed DEF on ABC, it's possible for them not to overlap. So let's try to see if that's even possible. So then we'd have EFD, right? We're assuming that they're not going to overlap, right? So then, this side equals this side equals this side, but we showed that that's impossible from proposition number 7. So it is a proof by superposition, but he goes, he does kind of use a proposition to help him out more, whereas the side angle side proposition was entirely one of superposition. So, therefore it's impossible for them not to overlap. So you essentially place one triangle on the other, it's exactly the same triangle. Furthermore, the sides are all equal, so the angles opposite the corresponding sides would be equal. So opposite 2 lines is E, opposite 2 lines is B, they're equal. Opposite 3 lines is A, that's equal to D. Opposite 1 line is C, that's equal to F. And today we know that as the side-side-side congruency, and it's pretty much a postulate, but I like how he kind of showed that it's impossible using this argument, so he kind of went a step up and made it more clear.